No, it really is it's a wonderful privilege to be able to be here and to say something about the time and the experience I've had of working with Malcolm for about 30 years. And I'll start my talk just with a little bit of scientific nostalgia, but then I'll move on to some modern science as well, as I think in both things honour Malcolm and his contribution, of course. So yes, I'm in the School of Engineering in the University of Newcastle. And as I said, I'll just start off my talk with just a little bit of nostalgia. And I just say one of the things that I appreciate about Malcolm in science is that every time he went somewhere, I always felt he left that place better or better equipped than it was when he first went there, actually. And I'm sure a lot of us have had to work with people in our lives where people move along very quickly and leave a trail of chaos behind them anywhere they go. And Malcolm was just the reverse of that, I would say myself. And one of the I'm going to be speaking mainly about the modelling side. I'm not going to say very much about carbon at all. I'm going to talk a little bit about the computer modelling side of the work. This is a picture of Malcolm. Malcolm at that time, this is in the 1990s, he always went 1980s, in fact, late 1980s. He always wore a three-piece suit to go to work, so I'm not quite sure how I managed to catch him in a somewhat ill-judged attire on that occasion. But that was on the... Malcolm was one of the main movers in getting our first supercomputer, as it was called then, in the University of Exeter. And that was the first time actually we'd ever been able to have a computer on which you could just either click on something or rather type a command and you could run your program immediately rather than having to put it into a queue and then wait several days for it to run. So this was a real sea change that Malcolm was really at the forefront of pushing in the University of Exeter. That's in 1987. No, that's Bob.
Yeah.
Yes, I used to have very dark coloured hair, which it took me by surprise when I saw that picture of myself. It's true. Right. But Malcolm actually continued with this, and with this theme of actually providing computer facilities. And in the mid-1990s, this was at the time when we had something called parallel supercomputers becoming very popular. And Malcolm organised Bob and myself into a consortium which gave us access to the first really big, powerful parallel computer in Britain. In fact, this is the grant award from the record of a follow-up grant to that, but Malcolm's first grant, I couldn't find a record of that on EPSRC's website for some reason. But that really, it really revolutionised all of the research that we were doing at the time, and all of Malcolm's PhD students and Bob Jones's PhD students really saw a massive change really as a result of that. And again, that was something that Malcolm really was at the forefront of pioneering and getting us organised into this consortium. As a result of that, Malcolm, of course, always kept telling us how short he was and making jokes about himself, but he was very pleased to actually achieve a world first for the largest calculation that had been done at that time in terms of the numbers of atoms using density functional theory. That was as a result of getting this time set up on this supercomputer. And I should say that that pattern really continued. He moved from Exeter to Sussex, and there was a very big improvement in computer facilities in Sussex, and then on to Surrey, and the same story happened there. And I always feel wherever Malcolm's gone, he's always left a legacy, if you like, of scientific computing behind him. So in our progress in this consortium, the name of the program that Malcolm and many of us here worked with is the program called AIMPRO. And just to show that we were in some respects doing very well on this national computer, this just shows the actual performance and what percentage of the potential power of the computer we were actually able to use. And you can actually see that there. You can see that AIMPRO actually in 2001 was actually leading the pack of being able to actually successfully use half of the peak power of the computer, which was quite a remarkable achievement at that time. Okay, let's just move past. Another innovation that Malcolm produced was a piece of software called CryPlot. And again, it's very hard to imagine what life was like in the 1980s, where just to be able to actually produce a picture of a molecule like this was actually a real nightmare. There was no computer package you could just draw something like that on at the time. And Malcolm produced some software that enabled us to produce all of these pictures of the systems that we were modelling. And there's a whole generation of people that use his software and actually still use part of that software, even quite recently, to generate some structures with defects in. And another slightly amusing memory I have of Malcolm was in the very early days in the 1980s. Again, our program in those days was so primitive, you couldn't just run the program. Every time you had to model a different system, you had to rewrite part of the program every time. So if you added a molecule, if you added an atom, you would have to rewrite a program and then compile it and then run it. And I remember just countless disappointments when you have to wait a week to run a program, and then you find it basically stale, and then you have to try it again. And just remember Malcolm's sense of humour at that time, as we all used to be struggling to try and get these runs through together. But so there was some disappointment at that time, but also a lot of fond memories of Malcolm sort of training us all to cope with disappointment as well as with success, actually. But overall, though, largely through these computer facilities that we had, life did actually get better. And through a series of improvements, both in the computers and in our computer program, we moved from a case where, this is one of Chris Yule's slides, in 1996, you could model a collection of 88 atoms like that. It would take you 3 weeks to do it. And now, on a simple PC, something like this can be done just in a couple of hours. It's really quite amazing how...
That was on the biggest machine that we had.
Yes, that's right. That was on the biggest machine. So you can really see how things have changed over the course of this career. And that really shows, really, that the longevity of Malcolm and his contribution to atomistic modelling. And also there's some element of foresight in it to try and do a very sophisticated calculation in the 1980s, when it was so hard to do that calculation. You could only model just a very tiny number of atoms, but so to actually choose to do a very sophisticated calculation on a small number of atoms took a certain amount of courage and foresight. But actually that's turned out to be the way that everybody now does the calculations today. So I think that's also reflects extremely well on Malcolm's judgment at the time. Anyway, life has moved on since then. So that was our record that we managed to achieve in 1997. That used about 3 months of our entire allocation on our national supercomputer to produce this publication in the 191st meeting of the Electrochemical Society. But since then, of course, this has become much more routine. Now, this is one of John Goss's figure from one of John's papers, to show you a defect in diamond, which is modelled in a 1,000 atom unit cell, and that's still a big calculation today, but that can be done in a much more routine manner. Right, and indeed now we can do calculations that go all the way up to thousands of atoms using a new technique that I'll talk about in a moment called filtration. And this idea of filtration was developed quite recently to enable us to do much larger calculations so we could model much more complicated systems. And part of that again was driven by Malcolm's work in graphite, where that was very important. I'll just keep an eye on the time on my phone there. Right. So that's just a little bit of just looking back and just noticing how Malcolm has always actually led to improvements, I would say, in every place that he's worked over many years. But I just want to talk a little bit now about something that we've been working on in Newcastle over the last couple of years. And that's looking not so much at trying to model bigger systems, but trying to improve the quality of the modelling we're doing so we can actually achieve a greater accuracy. The technique that we're using is this technique called filtration, which I'm not going to talk about in detail, but I'll just present the results and you can get some feel for how we're gradually moving the calculations that Malcolm is doing for many years and how we're moving forwards in those methods. So one of the questions that if you're an experimentalist, you always get asked, what are the error bars on your graph, how accurate are your measurements? And it's always a slightly difficult question to answer if you're a theorist and somebody says, well, what is the error bar on your calculation? Because sometimes it's quite difficult to judge how accurate a certain theory or approximation is in quantum mechanics. And so what was actually developed is something called a delta test, where what you basically do is you look at lots of different computer programs or attempts to solve nominally the same problem. The idea basically is you calculate the binding energy curve for your solid. So you plot the energy of your solid as a function of the volume, and you get your normal binding energy curve, and you can actually compare this binding energy curve from two different computer programs. So you can actually calculate the difference between the binding energy curves. You can integrate that over a certain range of volumes, a little bit on either side of equilibrium, and that would basically give you a delta value. And so what you could do is you could look at two different computer programs, you could work out this quantity, and that would tell you how similar or how different the answers produced by those computer programs actually are. And so we have this sort of picture that has built up, where you can have one program being judged against another. And so this would correspond to delta being equal to 0.3. That's comparing two different computer programs solving the same answer. And without actually going into this in a lot of detail, basically 0.5 or better is regarded as a very, very good degree of agreement. But then when people actually looked at these different computer packages, then what you actually find is that these values of delta do vary quite considerably. And the question was, well, what would we actually do with our software that we've been using for many years? Because our software was not designed primarily for accuracy, it was designed primarily to be able to model very large systems. So the argument that we've always used in our modelling consortium was it's better to do a 95% job on 1,000 atoms than a 99% job on 10 atoms, because 1,000 atoms bears a much closer resemblance to the system, which you really are trying to model. So what can we actually do to work on this delta value for our own code? And when you actually compare two different computer programs, there are basically two. There's the actual equation that you're solving. That's if you're assuming the two programs are solving the same equation, and there are really two sources or three sources of approximation. One is the potential that goes into the Schrödinger equation, the equation we're solving. One which is what's called a basis set, and that's just the approximation that's made to the wave function. And finally, there's just the precision of your computer program. If you're working out integrals or something, how accurate, how many figures do you decide to work them out to? And of course, there are some computer programs that always claim to be absolutely perfect in all of those aspects. So the errors can be made arbitrarily small by doing a better and better quality calculation just by changing the data, in the numbers in their data files. So it was a little bit of clean fun that you could have to start with in the early years of that, where you have several programs that all claim to give the right answer, and it turned out they actually all gave different answers. There was some good fun trying to see who was actually going to come out on top of that argument. But eventually that was all sorted out. And then, of course, all of the other programs then begin to try and compare themselves against this correct answer. You can really see, so this is CASTEP, which is not a package that we've used a lot. Malcolm used it once or twice in his career. But this number from CASTEP actually gradually improved from 6.5 to 0.7. I think it's been a better value published this year as well, or last year as well. Whenever you have something like this, you've always got to ask yourself, is this something real that we're doing? Is it really just a game? Whenever you measure anything in life, of course, everybody adjusts everything that they're doing just to get this one number right, and sometimes getting one thing right, you make other things less good at the same time. But nevertheless, this is the accepted benchmark that we're all having to work to. So the idea would be that you look at all the elements in the periodic table which are going across the bottom there, and you compare one code against another. And every element will have its own value of delta. So for every element you have a particular form of matter. So for carbon, in fact, it's graphite. For silicon, it's obviously your normal silicon structure. And you can compare, you can work out this value of delta for every element in the periodic table, and then you can basically average that to get your overall value of delta. So these are comparing two different computer programs. One is the one that we use ourselves, AimPro. The other one is Abinit. They're both being compared against something called V2K, which is regarded as being the correct answer for this benchmark. So just looking at this graph, you can see that the two curves basically have a very similar type of trend. That's because both calculations make the same approximation in potential, but different approximations in the wave function. But within AimPro, we're really interested in trying to make our wave function as accurate as we possibly can. So that's really what we're setting out to try to do. So it is certainly true that we were able to do these world record calculations in the 1990s. However, it would not be true to say that that was also the most accurate calculation in the 1990s. So the question is, would it be possible to develop our code so that we could routinely do a 1,000 atom run, but would also get a delta value which is as good as the very, very best? So that was really the challenge that we've been working towards. Now the next 5 minutes are quite technical slides, and some of you will understand what I'm saying very, very closely, and others will understand a little bit less, but I'll come back to the big picture maybe in about 5 minutes' time. So anybody who's used AimPro will know that you always have to generate something called a basis set, which is normally generated to work in a particular environment. So you can see there's lots of basis sets that's been generated for graphite. Basically, this one at the end here is the one that everybody uses, and that's believed to be the most accurate basis set in AimPro for graphite. We have different basis sets for diamond and so forth. So all of our calculations basically are dependent on getting a very good basis set to use. But part of the problem is that every time you move to a new material, you have to generate a new basis set. And obviously, if you're working in carbon, then you develop a lot of experience in that. And after a certain time, that's not such an arduous task. But if you suddenly want to move to a new material, then there's a lot of work to be done. So the question would be, is it possible to generate a basis set that doesn't depend on the solid? You can generate it from an atom and then use that basis set for any solid that contains the atom. So that was the question that we began to look at. So this is looking at an element which is scandium, I think, is that right? And we're looking at how the energy of this atom changes as you increase the number of Gaussian functions. You can actually see that actually as the number of Gaussians is increased, you actually get you get a convergence in energy. The energy change compared to the converged value becomes smaller and smaller, and you can easily converge that down to a microelectron volt. The problem is that even though you can do that for one atom, you would not be able to do that for a unit cell with 1,000 atoms. The calculation wouldn't be stable anymore. But nevertheless, that shows that it's possible with our approach to get microelectron volt convergence per atom. How can we actually take that across now into the solid? And that's really where this filtration idea comes in. So the idea is we use this new technique called filtration to start off with generating a basis set for an atom where the error for any atom in the periodic table will always be less than a milli-electron volt. And that may have a huge number of Gaussians, more than we've ever really used before. But this filtration method actually enables the calculation to be done with great stability. So that doesn't really matter that you have so many basis functions. Another parameter that we have to vary in our calculation is the angular momentum of the basis functions. We all know that in carbon, the velocity is related to S and P electrons. If you actually try and write down a wave function for a carbon in terms of angular momentum, in fact, it turns out you have to use D's as well as S's and P's, because when you get bonds forming, the atomic state become distorted and no longer have exactly the correct symmetry as they would for an isolated atom. So it's quite routine for people to use D-type basis functions to allow for this polarization, as it's called, when solids are formed. But in these new basis functions, we're able to go as high as K's. You might never have thought of a K-type angular momentum. The angular momentums are called SPD, FG, and then they just go on alphabetically after that. So it's FG, H, I, J, K. So we're going very, very high in angular momentum. That can now all be included automatically. And with some new coding, actually, we've made the calculations using those even quicker, in fact, than the ones that we're currently using. Right, let's not get into too much detail on that. So the idea really is that by generating this absolutely huge basis and using this filtration algorithm, which just chooses the parts of that huge basis which are important, you can actually do an extremely accurate calculation. Now, normally when people look at calculations, you often see this sort of progression. You have plane waves, which give a very, very reliable answer and a very accurate answer. That's one type of calculation. You have type binding, which is a much faster calculation, but it's something a little bit harder to set up because there are a certain number of parameters that you need to define your type binding, or there can be. And Gaussians, which is the method which we use in AIMPRO, is somewhere in the middle. So Gaussians actually are quite a bit quicker than plane waves, and type bindings are a lot quicker than Gaussians. But the penalty you pay, of course, is that type bindings are normally not as accurate as Gaussian calculations, and Gaussian calculations are not as accurate as plane waves. So normally speaking, when you move across from left to right here, then we'd actually say that this is the slowest, but it's also the most stable and the most accurate. This is by far the fastest, but possibly slightly less accurate and maybe less convenient if you're starting on a fresh element. But with this filtration algorithm, in fact, the argument actually is that we're able to generate this massive basis set, and the filtration algorithm enables us to use this, and by doing so we can actually get an agreement with a plane wave calculation. We can produce a delta if you compare computer programs with these two very different descriptions of the wave functions. The delta would be much less than 0.5, in which case you'd actually then be able to say that you're able to do this calculation actually at the same speed as this. But filtration also enables this calculation to become faster than it was before. So filtration actually enables you a Gaussian orbital calculation in principle to get a plane wave accuracy, but to actually achieve that at a type binding speed. So this is really quite a step forward. So we're using an idea that will both make the calculation more accurate and faster at the same time. Let's see, can we actually get that to work? So I talked about the idea of increasing angular momentum. So with carbon, if you use your D-type functions, that's L equals 2, we would normally use 40 functions for every carbon atom, and this is just the energy in a certain unit, Hartrees, of our 8-atom cell. This is silicon node on carbon. If you increase the angular momentum up to 3, so you use F-type orbitals, then in fact you end up with twice as many functions, and the energy, you can see, becomes a little bit lower. If you go up to G's, you end up with 140 functions to treat 8 atoms of silicon, and to treat each atom of silicon, but in fact the energy comes just a little bit lower again. Now, you can't go any higher than G's with a normal calculation because this is at the very end of our stability. We can't go up to H's without losing our stability. However, the filtration enables us to go up to J's, in fact, quite easily, and using this filtration algorithm, you can actually see that we were able to actually produce an energy which is lower than any of these. So the filtration algorithm has actually produced a more accurate, a lower energy, but it actually produces it faster. So that's really what we're exactly what we're looking for. So all the calculations that we would have done before would have produced an energy which is somewhat higher than this new one, Although, of course, all the calculations in the past, the energy is largely a systematic one, and when you actually look at a published energy difference, that energy difference will not be perturbed very much. However, by getting this extremely good converged value now, that does enable you to move to another element of the periodic table. So suddenly, if you want to model erbium or gadolinium or something which is much less familiar to us than carbon, you can actually take that step without having to build up this years of experience as to know what type of basis function are best used. So just for your interest, that this actually includes 480 functions for every atom. It's a huge number, but by the filtration algorithm, you just choose, of those 480, about 40. You choose actually the same number of degrees of freedom from those as you had in your original calculation, but you get a much better energy. So again, if you look across the periodic table with that, then you actually see we get extremely good agreement. It's exactly the same trend as this plane wave calculation. This really shows that the approximations in our code really can make our code agree to an extremely good extent with Abenit, which is a plane wave calculation. So you really can get the same degree of accuracy as something that would have been considered the Rolls-Royce, if you like, of atomistic modelling calculations. And the delta value, if you compare our code with this green code, is in fact 0.3 millielectron volts per atom. That's comparing using the plane wave code using the same pseudopotentials. The advantage, of course, with our approach is that we can actually improve the pseudopotentials and therefore get much closer to the absolutely correct answer as well. That's something which we're working on at present. So the conclusions really are, as a result of this, is that it's now possible, in fact, to use a really huge starting basis and to filter from that at relatively little additional cost. Therefore, all these questions that have plagued a lot of us over many years, trying to choose the perfect type of basis to do a calculation, are largely now obsolete. That will, as this new code comes into usage, then such questions, I think, will not be pressing in the way they have been in the past. So filtration, the technical point, is very different to basis set contraction. You're not just trying to make something go faster, you are actually making it better at the same time. So if you look in any books on quantum chemistry, you'll see lots of tables where you look at different energies of reactions for different basis sets. So all of those essentially are rendered obsolete by this type of approach. So AimPro now, we have a fully threaded version of AimPro. It works very well on workstations. Interestingly, the new version of the code is back down to 5,000 lines, which is what it was when I was doing my PhD. It grew to about 200,000 lines, but rewriting it again has mysteriously made it much shorter. I don't know what that means. I've become better at computer programming over the last 30 years gradually, but there we are. But much more aggressive use of modern Fortran in that process. So in fact, you can now get a new level of accuracy which was not actually achievable with the old basis sets. So now we actually have two versions of our code. The accurate one, which will achieve the delta values I've just been talking about, that will run at a similar speed to AimPro at present, but it will be very much more accurate. It should still be many times faster than other codes looking at moderate system sizes. And there's also a faster version of the code that can really try to compete in speed with tight binding, but you do lose a little bit of stability if you're going to do that. If you're really interested in carbon, then that would be absolutely fine. If you're trying to go all around the periodic table, that's much harder to use. So we're going to come to the end of what I've got to say. So that means I must have finished more than 5 minutes early, is it? It's because it's not waved at me.
You just hit 5 minutes there.
Sorry?
You just hit 5 minutes there.
Well, I'm going to spend a long time to go through my acknowledgements. So, Mark Rayson was one of the originators of the filtration algorithm. He's based in Newcastle, and I've used some of John's slides to illustrate the calculations. And Tiago and Andrew Lawson were two of the PhD students who worked on filtration. Bob Jones, as Chris said earlier, was my PhD supervisor, as well as Malcolm. The very, very first version of AIM-Pro actually originated, of course, with Bob Jones when it was about 1,000 lines long at that time. Chris Yules, of course, we've used some of Chris's slides, and some of Malcolm's group when he was at Surrey, and Alexandra Muse from Avero. But of course, finally, I just want to overall just to acknowledge Malcolm and his massive input into this work over really so many years. I'm sure we'll hear so much of what he's achieved scientifically in the rest of today. But I think also just in the way that he had the vision to choose the right technique at a time when it was not fashionable. And when I started my PhD, there were only 2 groups actually in the United Kingdom using this technique of density functional theory. There was one group in Cambridge, then there was us in the University of Exeter. And everybody else in Britain at that time were doing either recursion or type binding. It was this type of calculation. But Malcolm and Bob actually stood out against that trend. And now you find that density functional calculations are done in every physics, chemistry and engineering departments around the world. But that was a long shot, you might say, in the late 1980s. But that was a lot of foresight. And I think that Malcolm's drive to always produce good high-performance computer facilities in every university and department he's been has also been an immense benefit to all of his students and collaborators as well. And so really, I do want to acknowledge Malcolm's huge input into my career, starting off right from the very beginning when I was trying to learn how to write a computer program, all the way through until the last few years as well. And I'm sure that everybody who's known Malcolm would actually say exactly the same. Malcolm is a man who never blames you when things go wrong, because I've never been his PhD student, I should say. But as a collaborator, he's never blamed you when things have gone wrong, and he's always been very generous in his praise when things have gone well. And it's always been very good to work with him for many years. It really is a privilege just to come and just say a few words about him today. So I think I'll finish with that point.
Thank you very much, but I'll just bend the microphones because I've been told that the sound will be better like this.
Standing in the wrong place.
So, that's okay. So, do we have any questions? Roger.
Hello. Patrick, at my university, we've got many different groups using many different these packages, Quantum Espresso, Castor, AIM-Pro,
Yes.
Amongst others. What you've described here seems almost too good to be true.
Mm-hmm.
Do you think any of these other competitor bits of software have latched onto this, and will we expect that this filtration technique will become a standard in many of these other DFT-type packages?
I think it is true. I mean, I'm certainly aware of 3 other packages that have started to implement filtration. I know there are 2 packages in which it's got to quite an advanced state, and another one in which it got so far and then stopped. As to how far that goes, I mean, I honestly don't know. I mean, there are other types of technique that also try to produce. It's not technically filtration, which is a projection operation that we're doing. There are other techniques using something which is more akin to optimization as a way of generating 4 functions from a larger number. So there are techniques that follow sort of similar overall principles, but I think certainly I think that this is the most advanced implementation of this at present. Yeah.
Hello, Patrick. Thank you for your talk. This is Paul, Malcolm's PhD student at the University of Loughborough, and I've been using so far the old version of A Pro. Is there any opportunity for us to get the new one you just talked about?
Yes.
With the two versions which targets speed and accuracy?
Yes. So the first version of filtration was designed largely to try to model larger systems, but it didn't have this extra idea of projecting from a larger basis function. So that one has not come out through the door fully yet, but we're very close to getting there, and I will certainly be willing to hand that out.
You can tell that you're Malcolm's PhD student, because that's always the Malcolm question at the end of Patrick's talk.
Great talk, Patrick. Thank you very much. This is maybe a slightly boring question because I want to go back to one of your numerical slides. I think it was the Scandium one. And just out of curiosity, I think when you had 11, yep, that one. So if you look at the delta E for 11, that was pretty good. So why does it then go up again? Is there an easy reason for that?
Right. Well, it could be that there are a number of things that one could say about that. I mean, sometimes when you actually... Right. Yeah. So the idea is here we've got... This is quite a technical answer. So we have a certain number of Gaussians with their different exponents. So one could say, yes, I want to optimize all 21, if you're on the bottom line, 21 exponents independently. Well, we don't do that. We keep them in an even-tempered set, so each one is a certain factor times the previous one. So then you basically just got the first one, the last one, and the number in the middle, basically, as your parameters that you're optimizing. But then to make optimization even simpler, what we said is because we don't really, if we've got 10 exponents, we don't have to get absolutely the best 10. We don't mind if it's 15, but because we have this filtration algorithm. So what we do is we just choose the highest exponent to be a fixed number that you can deduce from the pseudo potential. Then we have then a single parameter optimization where we vary only the lowest exponent. Okay? But then that does lay you susceptible to this type of effect. Because if you just imagine it, let's suppose you wanted to fit a perfect Gaussian with exponent 1, and you're starting off with an exponent of 42, then you've got to choose your bottom exponent at just the right level, given the number of Gaussians you've got to hit on that magic number 1. Okay? And so you will get that type of effect happening. But the very fact that we're able to keep going all the way down to 20 means that if that effect happens, then you will see some slight non-monotonic behavior here, but by the time you get down here, then of course all of these are consistently under your microelectron volt level. And I think this is part of the problem with large basis sets, just trying to unambiguously define them without this slight uncertainty you get from this very corrugated energy surface. So that was our way of trying to solve that. But I think with a huge number at the end, I think that doesn't really become a fundamental objection anymore. Yeah.
I think maybe we'll... Just one quick comment on Quaiplot. I don't know if you remember, John, it's the worst code, Malcolm's code, that one for design. You had all these 3-letter codes, and at the start of our PhD, he gave us a lecture, and I've got pages of all these 3-letter codes, and it was impossible to use, but it was very, very powerful.
It's one of the things, if you actually want to generate an atomistic model with a screw dislocation or any different type of dislocation, I mean, Malcolm's software would always do it for you, wouldn't it? And then it would even pre-relax the structure afterwards. And so, if we hadn't have had that, I mean, it would have been a nightmare doing so many of these combinations. And again, I think that was something which Malcolm did that was sort of somewhat unsung, but it's been a huge benefit to many of us working with defects over many years.
Very quick benefit.
Yeah.
You mentioned in Quaiplot, you very briefly said someone had used it recently. Do you know who that was?
Well, I think Malcolm used it quite recently, actually. He told me that he still had a working version of it, actually. So.
Yeah.
But I haven't done a dislocation calculation in many, many years now, so I haven't done that myself.
Well, maybe we can thank Patrick again.